What up? What up? What up? We are in another wonderful video of products of fractions. We have done lots of stuff with fractions. So if you have not watched previous videos, please feel free to go do so because today we're going to just build on that. So I'm not going to dive in deep about the modeling and the things that we have done with fractions times whole numbers and whole numbers times fractions and fractions times fractions. Today, we're just going to talk about the patterns in which we see to kind of help free ourselves up. So, what I mean by that is, again, we might have an example of something like 2/3 times 1/2, right? So that's the products part, right? That's when we multiply. That is also where we might see the word of, right? Of also means to multiply when using fractions. We could also maybe even see the word by, right? Because it could be a concept of area. If I have 1/2 by 2/3, well, I am multiplying, and there's things that we've done to look at that. But in this video today, we're really just talking about the simple algorithm of being able to solve this problem. But let us at least start with, and I'm gonna get rid of this rectangle over here. Let's have us start off with just like some general observations about it, because that's always a good piece. That's always a good place to start, right? If we think about what's happening here, what we know about numbers, one thing is we know that 2/3 is less than 1. This is a value smaller than 1. And we also know that 1/2 is also less than 1. You might even want to say they are less than a whole. And that's what fractions are, right? They're parts of wholes. So when we're dealing with two numbers that are smaller than 1 and we multiply them together, then we actually know that our product is actually going to be smaller than either of the numbers we're multiplying by, right? Because if they were 1, well, 1 times 1 equals 1, right? If one value was larger than 1, 1 was 1, and 1 was larger than 1, well, then again, you can see I end at a product that's larger than what I started with. In this case, I ended at a product the same as what I started with. And when we deal with something that is smaller, then we'll actually end up with a product smaller, right? And we saw that in decimals all the time. With that idea that if I had 8 times 5/10, well, again, that is telling me I'm going to end up with something. Sorry, that was supposed to erase. Oops, sorry, not clear all drawings. Just there we go. This would again be something that ends up having a smaller value than 8. And we can do that math because we've learned that 8 times 5 is 40. And then I have one place value, so I need to replace one place value. So 8 times 5/10 actually equals 4. And you can see that is smaller. So the same rule applies to fractions because, well, fractions are equivalent to decimals. They are the same thing, just written in different forms, but they carry the same value. So that's just a really good observation to start with. And I always want to talk about that because it's really important that we think about that before we go into doing our math because it helps us double check our answers as well. So if I know that my answer when I'm done here is going to be smaller than 2/3, that's going to help me when I do the work. But again, today is just about the algorithm and what we've learned so far by finding patterns in the math we've done in the other videos. So again, hopefully you've watched those so you know what I'm talking about here. Is that in this case, we've learned that the reality is just to solve it, we literally can just start by multiplying the numerator, and that would be step 1. So again, 2 times 1 gets me 2. And then if we thought about our second step, we literally are going to just multiply the denominator. And that would be 3 times 2. And that gets me 6. And then we are done. That's it. It's actually more like a two-step process, but we'll just say done. I'm done. Now, we have looked at how this works. We've modeled it. We've done all this work, so that's fine. But today's video is really like, what is the algorithm? Let's just practice it. Let's get it done so that we can get an answer. And again, if we looked at this idea of my estimation, maybe that's step 3, double check your estimation. I know my product was going to be smaller than 2/3, so let's see, 2/6 and 2/3, those are smaller because the numerators are the same, but the pieces, but I'll just draw it real quick just to prove it. So there's 2/3, and then here's 2/6. So 2/6 is much smaller than 2/3, so this does work, it pans out. Okay, so maybe it's not just done smiley face, but it's more like, hey, double check. Like, double check with that whole idea of value. Double check, double the value, double check the value. I don't know, right? All right, let's try another one. Let's just play around. Let's keep going. It's always about practice. If you feel at any point you're just like, oh, let me pause this and do it, do it. So 5/9 of 1/9. So again, one thing we're going to see in times of fractions again is that special word of referring to a multiplication process that happens when you're working with fractions. So that's where it gets a little tricky. You can see of in other word problems, but if there aren't fractions around, it might mean something different. So it's only a really good clue when there are fractions. When there are fractions, then we know when there are fractions, we know of is a good clue to multiply. But again, here's that case then. I'm really thinking 5/9 plus 1/9 or plus, wow, times 1/9 after all that. So again, the rules. So let's just multiply the numerators. That gets me a 5. And then we're going to multiply the denominators. That gets me an 81. And I am done. I can double check again. I started at 5/9. My answer is actually going to be smaller than 5/9. So 5/9 is larger than 5/81s. And that is true because, again, think of what we know here. We actually have the same number of pieces. I don't even have to model this. We have the same number of pieces, but the pieces are cut into different sizes. So I have at 5/9, right? That means I took a pizza and I shared it with 9 people. I don't just pretend that's 9, please. I'm not even going to try to cut that. You know how I feel about a circle. And I have like 5 of them, right? So I don't know. We have this much. And then at 81st, that's literally like saying I have to take a pizza and cut it into 81 pieces. Again, seriously, this isn't really 81. It's not even accurate, but I think you get the point. It's going to get so much smaller. And then you have 5 of them. So that would maybe only be like a smaller section like this. So you kind of know that without modeling by knowing, again, that the larger the denominator, the smaller the piece. If I take something and I cut it into 9 pieces, those pieces will be larger than if I took the same thing and cut it into 81 pieces, right? That's going to get tiny, tiny. 9 times smaller-ish, kind of, maybe. Anyway, that's that. So that one checks out. So 5/81st, there's my answer. So again, let's play around, right? It feels pretty comfortable. Let's say, for example, we had 3/9 times 6/9. So I just did 2/9. Not 2/9, but 2 numbers with 9. So I'm gonna do that. I don't want to do it. Let's do the 8 just to mix it up. Okay. So again, we're gonna multiply the numerator. That's 18. And then I'm going to multiply the denominator, and that's 72. And there we have it. There's my answer. Yay. And again, we can look at that again. It's 3/9 and 8/72, right? We want to make sure that 3/9 is larger. We want this value will be smaller because I'm multiplying by 2 numbers smaller. I don't know. Gosh. 1, 2, 3, 4, 5, 6. 7, 8. Yeah, there's my 9 pieces, or my 9 pieces, and I have 3/8. Okay. And then I'm gonna take something the same size. I'm gonna cut it into 72. Oh, goodness gracious. Let's see. That's gonna be 9 this way. I'm just gonna copy that. That'd be 9 on this side, and then that would be 8 on this side. So I'd have to go 4 and then 8. So there's 72, and I have 8 of them. So 1, 2, 3, 4, 5, 6, 7, 8. So that's just this section here. So we can see by the model, right, that this is 3/9 is a lot larger than 8/72. Okay, cool. Let's just do one more because honestly, why not? Because we're flying through these, right? Let's say we have 3/5, and we have to multiply it by 11/12. Wow, that does not say 12. So again, we are going to multiply the numerators. 3 times 11, that equals 33. This is a good thing I practiced all this single digit multiplication all year. And then we're going to say 5 times a 12, that equals a 60. And in case you don't see that, again, I like to expand it out. That is a funky looking plus sign, right? 10 plus 2 is the same thing as 12. I say 5 times 10 is 50. And then I say 5 times 2 is 10. And when I add those together, that's how I got the product of 60. In case 12s aren't your thing yet, that's fine. But in most of these cases, we're going to be working with that in there. So, heck, there you have it. Let's just do one more funky one for fun because sometimes this might happen. What if this happened? What if this happened? Oh my gosh, what would you do if this happened? You probably wouldn't panic. Whatever, here it is. So in this case, we have some parentheses, we have some order operations, we have an addition. So I'm gonna go ahead and think about what's happening in here first. It's actually asking me to add 1/3 plus 1/3. Again, remember, I want to make sure my numerators are compatible, which they are because they are the same. So if I have a third plus a third, I just get 2/3. And then I'm gonna take that and multiply it by a half. My answer will be smaller than a half. 1 times 2 is 2. 2 times 3 is 6. That is 2 6. Again, that would be a half. And then if I had to do sixes, it would be like this. I have 2 of them. So again, even though my models are not super accurate, they are good enough for me to see that 2 6 is smaller than 1/2. So that does make sense. I do get smaller when I multiply. All right, now that's it. I'm done. I don't know why I wanted to throw that in. Who knows? Maybe you'll see problems like that. Maybe with more complexity. That one was pretty simple. Maybe they might have denominators that aren't the same in the parentheses. So, going back to do that job. I'm babbling. Get to work. Do a great job. You are awesome. Keep it up. All the other great things that you can do. Keep doing math. Math, math, math. Bye.